We have now seen what tasks and task networks are and how we can use methods to decompose these tasks into subtasks in a network. That means we have the basics for our new search space: task networks as search nodes and methods with decomposition as state transitions in this new search space. That means we can now define domains, problems, and solutions to planning problems. Let's start with STN planning domains. These are the reusable components that we can use to define many problems. And an STN planning domain is simply a pair consisting of a set of strips planning operators, that's the set O, is here, and it has also in addition a set of methods, STN methods, that's the set M. So you can see it's an extension of the strips planning we've seen before, because the operators still make up the domain, but in addition to operators we now have a set of methods. That's really all there is to STN planning domains. Now, one special case are total order STN planning domain, and we say that a domain D is a total order STN planning domain if every method in its method set is totally ordered. And later, when we look at STN planning algorithms, we will see that totally ordered networks are slightly easier to deal with. So first, we will have this as an algorithm, and secondly, we will introduce an algorithm that solves partial order STN planning problems. Now that we have defined STN planning domains, we can turn to STN planning problems. And an STN planning problem is a four-tuple consisting of Si, Wi, O, and M. And I'll explain these four components now. The first component, Si, is the initial state of the world from which we are planning. So this is a set of ground atoms, and that means it's just like for a strips planning problem, which also had an initial state consisting of a set of ground atoms. What is different here is that we don't have a goal component as part of our planning problem. Instead, we are given an initial task network, and that is what Wi is. So the problem then consists of refining this initial task network into a plan. And you will see that this initial task network often consists of just a single task, in which case this forms the root of our decomposition tree. The remaining two components, O and M, simply form an STN planning domain that we also give as part of our planning problem. So you can see an STN planning problem is not very different from a strips planning problem. We still have an initial state and we still have a domain. Of course, the domain is now a domain consisting of operators and methods. What's really different is that we don't have a goal, but an initial task network. And as for planning domains, we have a slightly simpler version here, namely a total order STN planning problem. A total order planning problem is one where both the initial network and the domain are totally ordered. So in the domain, all the methods need to be totally ordered, and in the task network that were initially given, all the tasks must be totally ordered. If this is the case, then our planning problem is totally ordered. STN domains and problems were quite straightforward and should be easy to understand. STN solutions are a little more complex, and the reason for this is simply that the definition is the blueprint for the algorithm that will follow. So understanding this definition will help you understand the algorithm. What we need to define here is the following. We need to define for a given planning problem consisting of initial state, initial task network, operators, and methods, when does a task pi consisting of actions A1 through AN constitute a solution for this STN planning problem? And this is the case if one of the following three conditions hold. And the first condition is quite trivial here, namely, if our initial network Wi is empty, so there were no tasks in the network, and our plan is also empty, then this plan constitutes a solution for this network in the planning problem. So that's quite obvious. If there's nothing to do, doing nothing is a solution for that problem. The next condition is a little more complex. So suppose there is a primitive task T in our network, and that task has no predecessors in the network. So it's one of the first components in that network. Also suppose that A1, the first action in our plan, is equal to t. So this action accomplishes this first task in our network. And suppose it is applicable in Si, the initial state. Then we can say our plan consisting of A1 through An is a solution to our planning problem, including the network Wi, if the following conditions hold. If the modified plan, pi dash, consisting of the actions A2 through An, so that's all the actions apart from the first one, is a solution for a modified planning problem. And this modified planning problem simply starts with a different initial state, namely the state that we get after applying the action A1 in our previous initial state. So we take the successor of our initial state given our action A1 as our new initial state in our new planning problem. And we remove the task T from our task network. And of course we also remove all the edges connected to T. The operators and methods remain the same. So if our slightly shorter plan is a solution for our modified planning problem, then we know that the longer plan is also a solution to our original planning problem. And the third alternative in our definition follows a similar pattern. Now we assume there is a non-primitive task T in our network. Previously it was a primitive task, now we're looking for a non-primitive task that has no predecessors in the network. So we take one of the first tasks, this time it's non-primitive. Now suppose we have a method M that is relevant for this task, that is, there is a substitution sigma, such that sigma of T is the task of the method. And suppose this is applicable in our initial state. Then our plan pi is a solution for our original planning problem if it is also a solution for a modified planning problem. And this modified planning problem consists of the same initial state, but then we have to decompose the task network Wi, which contains the task T as one of its first tasks, using method M and substitution sigma. And this gives us a new task network that we take as part of this modified problem. And again, the operators and methods remain the same. So if our plan pi is a solution to this modified problem, then our plan pi is also a solution to our original problem. What we have here are three alternative cases, namely the task network is empty, which means there is no first task in the network, or the task network has tasks that are first in the network, and they can be either primitive or non-primitive. One of these three cases must always hold. So one of these three branches in the definition is always applicable. And as I said before, the algorithm that we will see for solving STN planning problems will closely follow this definition.